All right, good evening, everyone. It's Tuesday night at 8 p.m., and I'm here at the Leitner Observatory ready to do the public night live stream. How's everyone doing tonight? It's a chilly, rainy, windy night here in New Haven, so I'm not out on the observing deck, but I've got the live view from the outdoor camera right here. And you can see the abandoned observing deck, a little bit wet, but not quite as bad as earlier today when it was raining pretty hard. You can see down towards Fairhaven, and you can see the I-95 bridge over in that direction. And I can see some clouds over just above the trees, so I don't expect to do any observing tonight. I'll go out and look at the sky before I go home and see if it's clearing up, but not expecting to do any observing for the live stream or for my class, for my observing class tonight. So instead, I thought I would talk a little bit about black holes. At the end of the live stream last week, I was talking a little bit about the Nobel Prize in Physics that had just been announced on Tuesday last week for the discovery of a supermassive black hole at the center of the Milky Way, as well as some theoretical work by Roger Penrose explaining that black holes actually could exist, that they were predicted by general relativity. So it was worth looking for evidence of black holes. Really massive objects, very compact, that might be in binary star systems. No one had the idea of black holes in the center of galaxies at that time. But there were some suggestions that there may be some binary stars where a star was orbiting a dense, massive, unseen companion. And it turned out that those turned out to be black holes, things like Cygnus X1, SS433, a couple of examples, a couple of sort of technical, nerdy examples like that. Anyway, so I'm going to start by showing some images that I took last week when Mars was very close to the Earth, and then talk a little bit about what's up in the sky this week. And then I'm going to talk a little bit about the Nobel Prize discovery, the actual discovery of the black hole at the center of the Milky Way, and the process that the astronomers Genzel and Getz went through to get the data and see the stars orbiting around the unseen black hole at the center of the Milky Way. And then I'm going to show our black holes show. So for viewers who have been to the Leitner Observatory and Planetarium on a public night in the not too distant past, you may have seen this Planetarium show that we have produced by the Denver Museum of Science with Liam Neeson as a narrator about supermassive black holes. And so I'm going to show that show with a little bit of commentary here at the end of the live stream. I'll be watching the YouTube live chat from time to time, so if anyone has any questions about what's up in the sky, about the Leitner Observatory, about astronomy, getting into astronomy, about black holes, about the planetarium show that I'm going to show, by all means type them in the chat, and I'll keep checking and try to answer any questions that I get. So let me switch over to my computer desktop here so I can show you the pictures of Mars that I took last week. So on Monday night last week, I did some observing with my students in my observing lab, and we took some images of Mars through our 12-inch telescope and got images that looked like this. Right? So this is actually a very good image. This is among the best I've ever seen Mars from the Leitner Observatory. So Mars was at closest approach around 10 o'clock in the morning on Tuesday or so. And so this was an image that I took on Monday night around 11 p.m. or so. Since Mars is opposite the sun in the sky right now, the Earth is between Mars and the sun, and that's when we're going to be closest to Mars, all other things being equal, is when we pass Mars in the orbit. So we're going around on the inside track at a distance of 1 astronomical unit, or 93 million miles from the sun. And then Mars is out at about 1.4 astronomical units, a little bit further out. And as we swing by, the distance from Earth to Mars is then about 0.4 or so astronomical units. As I said last time, when we were actually looking at Mars at the very end of the live stream last Tuesday, Mars is in an elliptical orbit. So sometimes it's closer to the sun, sometimes it's further away. All the planets around the sun are in slightly elliptical orbits. some more so than others. The Earth is in a fairly circular orbit, so is Venus, but Mars and Mercury and Pluto, if you count that as a planet, it's a dwarf planet, right? An ice dwarf. Those planets are in very elliptical orbits, so their perihelion distance when they're closest to the sun is significantly closer to the sun than the aphelion distance when they're furthest away from the sun. And this year we had a Mars opposition when Mars was close to us around the same time that Mars was at perihelion. It's a little bit closer than average, not dramatically closer than average. There's a little bit of hype associated with these perihelion oppositions, but it definitely does look better and looks brighter and bigger in a telescope. And so you can see some more details. Fred made a comment. He had a good observing session with Mars after Tuesday's session. Yeah, it cleared up okay on Tuesday, and it was a nice evening. And I stayed up and did some observing with my students and then looked at Mars and Jupiter later in the evening. So I'll show that image here in a second. So this is an image from Monday night. And so is this image. This is also an image from Monday night. And so you can see how much Mars rotated over a period of about 2 hours, from around 10:30 to around 12 o'clock or 12:15 or so in the evening. And in terms of the details that you can see, I know I talked about this last time, but you can see the south polar ice cap. You can see some of the dark markings on Mars. You can see that light area, which is Hellas Planitia. It'd be interesting actually to try and look for the volcanoes on Mars. So Olympus Mons, some of the big volcanoes that are just sort of around the edge. The Mariner Valley, I think, would be interesting to see at opposition in one of these high detailed images. On Tuesday, I took an image. Tuesday, not quite so late in the evening. There we go. So I took this image on Tuesday night last week. So this was a little bit closer to closest approach. It looks very similar to the last image. The color is slightly different. It's rotated slightly different because of how I had the camera and the telescope set up. But a very good image, I think. Probably the best image I've ever seen from New Haven of Mars. You can see quite a bit of surface detail. Sometimes when we have these oppositions, and this happens about every 2 years and 2 months that we swing by Mars in our orbit, when Mars and the Earth and the Sun line up, and we have a good view of Mars for about a month or so. Sometimes when that happens, the weather on Mars is not so good. Mars is known for its global dust storms, and that can obscure the surface features of Mars, and so you don't get quite as nice a view as we do right now. Today actually is Mars opposition. So right now, today is when Mars, Earth, and the Sun are closest to being in a straight line. And it was a little bit closer last week because it was a little bit closer to perihelion. So it's moving a little bit further away from the Sun, a little bit further from us, but we're in line with Mars tonight. So still a good time to look at Mars, and I think if it's clear any night this week, I encourage you to go out and look for that bright red spot that's opposite the Sun. So rising at sunset, highest in the sky at midnight, setting at sunrise. And if you have a telescope, take a look at it through the telescope. And if we have any clear nights this week, I will try to take some more pictures with our telescope here. Maybe I'll actually, in addition to taking pictures with the 12-inch reflector, I'll try taking some pictures with our 8-inch refractor, which actually provides really nice high magnification views of the planets. It's a little bit tricky to use because it has this old-fashioned motor-driven gear system for making the telescope track, and it doesn't always track perfectly, but it might be fun to try to take a picture of Mars at this opposition with our refractor. Refracting telescopes, of course, use a lens to gather the light and magnify the image versus a reflecting telescope that uses a mirror. And most of the telescopes we use here are reflecting telescopes. The bigger telescopes are reflecting telescopes. But we do have this historic 8-inch refractor, which is in the east dome. You can't quite see it off the edge of the camera over there to the left. But we have a bigger dome with an 8-inch refractor that's very long. We use that a lot for visual observations of planets and the moon and double stars and things like that. And then we use our reflector, our 60-inch reflector, to mostly take images with a digital camera for advanced labs and student research and things like that. Okay, well, let me talk about what's up in the sky this week, and I will briefly bring up the sky calendar like I did last time, and then switch over to my simulator to talk a little bit about the constellations that are out. So this is the same map that I showed last time. This is the evening sky map for October. And I like these maps because they're concise. You get all the data you need. You get all the information you need on one page, front and back. It shows you what constellations are up at 8 p.m. Early in the month, and then at 7 p.m. later in the month. So we're kind of in mid-October now. So this is more or less what the sky looks like around 8 p.m. or so, right about now. So we still have the summer triangle out, so not quite directly overhead anymore. Now they're a little bit west. These three stars are a little bit west of directly overhead. So the bright star Vega, Deneb, and Altair. You can see where Jupiter and Saturn are. Now Jupiter is much brighter than Saturn, and then Mars is much brighter than Jupiter right now. So Mars will be the brightest thing, and then Jupiter. And then I don't think Saturn is even as bright as the stars in the summer triangle, maybe about as bright as Deneb. Saturn is, of course, much further away. It's smaller, so it doesn't reflect as much light that gets to us as Jupiter does. So Saturn, Jupiter, and Mars are all close to the ecliptic. This is a line that astronomers project up into the sky that shows the path of the sun over the course of a year. It's really the plane of the Earth's orbit projected up into the space, up into space, up onto the stars. And so we keep track of the positions of the sun and the moon and the naked eye planets as they move around through the constellations of the zodiac, the constellations that line up with the direction of the ecliptic. So we've got Jupiter in Sagittarius here tonight, Saturn kind of between Capricorn and Sagittarius, and then Mars over here in Pisces. The way that you use this map, by the way, if I haven't mentioned this before, is you could lie on your back and hold it up and look at the sky, and the horizon is all around you. If your feet are pointing south, then south is at the bottom of this image, and if your head is pointing north, north is at the top of this image, and this is more or less what you'd see. I think a better way to do it is to face a particular direction on the horizon, north, south, east, or west, and then rotate this map so that that horizon is at the bottom of the image. And then you can see, okay, there are the bright stars in Aries, and then when you face south, you can say, oh, there's Jupiter and Saturn and the bright star Fomalhaut in the southern fish, Pisces Austrinus. And then you can look to the east and see things like Hercules and Ophiuchus. And you can look to the north or the northwest and potentially see the 7 bright stars in the Big Dipper. At our latitude, we never lose the Big Dipper. It never goes completely below the horizon, even in the winter when it's low. It's just harder to see if you have buildings or trees or structures in the way. May and April is really the best time to look for the Big Dipper at sunset, because then it's going to be basically overhead, a little bit north of overhead, depending on your latitude. You can still see Cassiopeia, right? So there's the 5 stars, the zigzag of Cassiopeia, like so. And there's kind of a line of bright stars that you can follow that lead you along the Milky Way. So the summer triangle is in the plane of the Milky Way, Deneb, Vega, and Altair. And then if you look to the north, and in this case northeast, you see the 5 stars that make up the M of Cassiopeia. Those are in the Milky Way. If you keep looking down to the northeast, you can see the bright star Capella coming up now. And then if you go the other way and look to the southwest, you'll see the Teapot. You'll see the bright stars in Sagittarius that make up the Teapot asterism. The supermassive black hole for which Genzel and Gez won the Nobel Prize this year is in this direction. It's actually very close to the end of the spout of the Teapot. Of course, we can't see it with visible telescopes. There's too much dust and gas between us and the center of the Milky Way. We need infrared telescopes or radio telescopes to peer through the dust and see to the center of the Milky Way. Okay, let me switch to the sky simulator and point out a couple of other things. Actually, before I do that, there's one other thing I wanted to say about the sky map, and that's to look at the calendar here, see if there's anything interesting coming up. So we've got Mars at opposition here today. Let's see, Mars nearest to Earth on the 6th, and then Mars at opposition on the 13th at 23 hours universal time. The universal time, that's basically Greenwich time or London time. This is the brightest the planet will appear until 2035. And then next week we have the Orionid meteor showers. So the phase of the moon should be good. The moon shouldn't be too bright on that evening on the 20th, right? We have a full moon on the 31st. So I guess it's actually a blue moon this month. We have a full moon on the 1st of October, and then a full moon again on the 31st of October. So colloquially, you have a blue moon when you have 2 full moons in a month. Now, the average time between full moons is 29 and a half days. So that could be 20 days or 30 days. On average, it's 29 and a half days. So this is really only likely to happen in a month with 31 days. And it's going to happen if you have a full moon on the 1st of the month, and then you'll have it on the 31, the last day of the month will also be a full moon. So on the 20th, we're going to have like a crescent moon. So it'll be set by the time you would go out and see meteors. For the meteors, it's best to go out after midnight and just look up. Don't use binoculars, don't use a telescope. Go out after midnight if it's clear. You'll see meteors all over the sky, and you get about 20 per hour on average with the Orionids. So not as many as with a bright shower like the Perseids in August, where you get 60 or 70 per hour, or the Leonids in November. The Perseids and the Leonids are my favorite annual meteor showers. So if it's clear, I usually try to go out to see those. The Perseids happens to fall on my birthday, so that's always nice to get to celebrate my birthday with a camping trip and a meteor watching party. And then I also have fond memories about watching the Leonids. The Leonids in November, it's around November 17th, is it's cold, right? So you have to go out prepared with your down jacket and your thermos of hot chocolate to enjoy the Leonids. The Leonids also from time to time are a meteor storm. Now, we're not predicting a meteor storm for this year, for 2020, but periodically, sometimes we hit a dense clump in the stream of the comet that seeds the Leonids meteors. Also not expecting that for the Orionids this year. I don't know, if it's clear, I might go out and take a look. I'll definitely set up my all-sky camera that night and see if I get any really bright meteors. Let it run over the course of the night and see if I get any really bright meteors that night. Okay, now I'm going to switch to Stellarium. Okay, and just sort of point out a few sort of specific things that are up in the sky, and maybe point out a few things that you could see if you have a pair of binoculars or a small telescope. So here's the sky right now in New Haven, so around 8:30 or so, October 13th, and I can kind of drag the sky around and see different directions. There's Mars over there in the east. It is higher than it was at this time last week, so it's getting a little bit easier to see. It should be more or less opposite the sun. Maybe not exactly opposite the sun because it's not exactly in the plane of the Earth's orbit today, but so it's a little bit below the plane, so not perfectly in line with the sun, but aligned in this direction with the sun. And it's going to continue moving to the west relative to the stars night after night. So it's actually going to get higher and higher and then start turning around and going backwards the other way. Okay, so Jupiter and Saturn, I pointed out before. Let me turn on the constellation lines and labels and point out again the Milky Way. So if you do have a pair of binoculars, scanning along the Milky Way is a really great idea, is a really nice treat. And I'll point out a few things that you can see with binoculars as you kind of scan along through the Milky Way. So when you start to get to the summer triangle, you can see there's the bright star Altair. And not much around Altair, but it's kind of a good reference point. So identify it with your binoculars and then you can move on. If you kind of go up and to the right from Altair, you would see what's called the coat hanger cluster. So here it is right here. Now it's not a true cluster, it's just an asterism. It's just a pattern of stars in the sky. but it is remarkable. I have students who tell me, yeah, these constellations don't look like what they're named for. Asterism is a pattern of stars versus a constellation is an area of the sky. And asterisms tend to look like what they're named after. They're modern. They tend to be modern star patterns. So coat hanger cluster, you can see the flat part there that you'd hang your coat on, and then you can see the hook right here. And this is not a true star cluster, although some of these stars are associated with each other. They're a co-moving group, but this isn't a true star cluster like an open star cluster, like I'll show you here in a minute. We keep going up the Milky Way through the Summer Triangle. Right sort of in the middle of the Summer Triangle is the double star Albireo. Now, you need a decent telescope to resolve this double star. But if you have a telescope that can provide at least 60 or 80x magnification, you should be able to see the two stars split. So we've got Albireo A and B, and amateur astronomers call these the red-blue double because the brighter one has kind of a yellowish, reddish cast, and the fainter one has kind of a bluish cast. We now know these are not a true binary system. We thought for years that maybe they were. But recent discoveries by the Gaia spacecraft, a space telescope that measures the positions of stars very accurately and their motions through space, discovered that these two stars are moving in different directions. So they're not actually orbiting around their common center of mass like true binary stars. Anyway, if we keep scrolling up through the Milky Way, through the Summer Triangle, some of these nebulae you wouldn't be able to see with binoculars. Like here's the Crescent Nebula. You would need to take a picture with a bigger telescope. You need to take a long exposure. It's not bright enough to see with your eye at the eyepiece of binoculars or a telescope. The Crescent Nebula is really interesting because it's associated with a Wolf-Rayet star, a high mass star that's losing mass. So maybe I'll talk about that at another time, and we'll try to take a picture of this, maybe with our 16-inch or our 12-inch telescope. But I want to stay I want to stay focused on things you can see with binoculars, and that would include things like star clusters. So here's the M29 star cluster right over here. Really beautiful little star cluster, small, bright. Don't think it has a colloquial name, but it's right there in the middle of Cygnus the Swan. There's Cygnus the Swan right there. So you see Deneb is the tail and Albireo is the beak. And there's this bright star kind of in the middle called Satur. And if you look a little bit to the left of that, you'll see the M29 star cluster. So very nice little star cluster. And there are many of these little star clusters along the plane of the Milky Way. Speaking of objects you need a telescope to see, here's the North American Nebula. So really big H2 region, ionized hydrogen cloud that you would need a telescope to see. But anyway, let's keep scrolling over. And now we're getting down towards Cepheus and Cassiopeia. And there is a really great and famous object you can see with binoculars just off of the Milky Way near Cassiopeia, associated with the constellation of Andromeda. I know I've talked about this before. So this is the Andromeda Galaxy. This is a galaxy you can see with the naked eye if the sky is really dark where you are. You can definitely see it as a little smudge of light. And it's easy to see through binoculars. It's easy to see through any size telescope, even a small 3-inch telescope. Looks great through our 12-inch Newtonian telescope. But now, of course, you won't see that much detail and you won't see the colors when you're looking with your eye at the eyepiece of a telescope or through binoculars. You can see a sort of a gray smudge of light, which is mostly coming from the bulge of the galaxy, which contains billions, tens of billions of stars, tens of billions of old stars. If you're looking specifically for the Andromeda Galaxy, there's a trick that I teach people, which is to look for the square of Pegasus over here in the east. So 4 bright stars that make a diamond or a square shape. And then if you take the brightest star to the left, you can count 1, 2, 3 bright stars over. You can do this with binoculars. I've done this, I did this last week. And then you can count 1, 2, 3 stars up. And then that's the anchor star for finding the Andromeda Galaxy right next to it. So one last object I'll point out as we kind of scroll around the sky is this little star cluster that's between Cassiopeia and Perseus. So if I zoom in a little bit here, you can see kind of a clump of stars right there. Keep zooming in. And this is the double star cluster. Two star clusters, one of them is called H Persei, the other is called Chi Persei. And two beautiful little star clusters. They look great through our 12-inch telescope or one of our 8-inch Schmidt-Cassegrain telescopes. They're a little dimmer and smaller in binoculars, but you can still definitely see them. And it's called the double cluster because you've got two star clusters right next to each other at about the same distance, so they've got similar brightness. So two pretty little groups of stars right next to each other. Okay. Anything else I want to point out? There is a star cluster over here in Perseus that's much bigger, but I'll stop talking for right now. And maybe I'll do some more star lore about what's coming up over here in the east and the northeast in a future live stream. But before I run out of time, I want to jump ahead and talk about black holes. So I was really excited about this last Tuesday when I heard that the Nobel Prize in Physics was being awarded for theoretical research and actually observational discoveries involving supermassive black holes. So probably you heard this in the news as well. This is the official announcement for the Nobel Prize in Physics 2020. So Roger Penrose, very famous scientist, mathematician, physicist, computer scientist, philosopher, has done research on artificial intelligence. Very important thinker of our time. Professor at Oxford University. Got 1/2 of the prize, so however many millions of dollars it's up to now, gets half of the prize and gets a gold medal and gets a trip to Sweden. And then the other half of this prize was split by two observational astronomers, one in Germany and one in California. So Andrea Ghez, astronomy is a small field and we all sort of know each other or know people who know each other. So I've met her a couple of different times. I wouldn't say she's a friend of mine, but she's an acquaintance. So it's always fun when an acquaintance or a friend gets recognized for hard work and an amazing discovery like this. And I heard only the 4th woman to get the Nobel Prize in Physics. I meant to look up, I know the first one was Marie Curie, of course, for radium. I meant to look up the others, the other physics Nobel Prizes, but there was someone who won a Nobel Prize for lasers a couple of years ago, and there was a group that shared the prize, and I know that one of them was a woman, but there's one more that I don't know. I should go look it up. So that's really great and very exciting, and I've been hearing about the observations made from the Keck Observatory in Hawaii of the stars orbiting around the supermassive black hole at the center of the Milky Way for, well, it's been 20 years now that Andrea has been doing these observations. So I'm not really going to talk, if people have questions, I'm happy to talk about some of the other aspects of the Nobel Prize, but I mostly want to focus on this, the measurements that went into the discovery of the supermassive black hole at the center of the Milky Way. Now, of course, we know that most big galaxies do have supermassive black holes at the centers, at the very core of the galaxy. And this is probably a consequence of how black holes form, it's probably a consequence of the way galaxies form, the way that really massive stars form at the very early phase of a galaxy's life, of galaxy formation, right after the Big Bang. And very large black holes are made, and at some point they merge to form a supermassive black hole. There's basically two families of black holes, right? There's the supermassive black holes that are maybe millions or billions of times the mass of the sun. And then there's the stellar mass black holes, which are left over when high mass stars go supernova. So those are a dime a dozen. They're orbiting all out here in the Milky Way with us. A lot of them are out in the halo of the Milky Way. We know about quite a few of them. And then these monster black holes that are at the centers of galaxies, we don't understand them as well. And so getting direct evidence, observations of one, is a big deal. So how was this done? Well, this was done starting, the early observations were made using the Keck telescopes on Mauna Kea in Hawaii. And Keck is crucial to this discovery in a couple of different ways. For one thing, as I said, we can't really see the center of the Milky Way in visible light, the light that you see with your eyes, just because there's so much dust and gas between us and the center that visible light is scattered or absorbed, and we just can't see it with visible telescopes. Keck has the ability to look at near-infrared light as well as visible light. So these two 10-meter diameter telescopes, for a long time the biggest telescopes in the world, not anymore, but for a long time the biggest telescopes in the world, were able to use infrared light to study the center of the Milky Way and look at clusters of stars moving around in the center of the Milky Way. But there's another important contribution from Keck, which is that Keck has an adaptive optics system, which allows you to remove the twinkling of the atmosphere. Now, the Keck telescopes are on top of Mauna Kea, 13,000 feet, this dormant volcano in Hawaii, which is already at high altitude in a place where the wind blows very stably in a laminar, not in a not turbulent way, in a very smooth way so that you don't get a lot of atmospheric turbulence above the mountain and above the observatory. So you already get very sharp views from the top of Mauna Kea, but most big research telescopes today will have adaptive optic systems where you either are looking at a bright star and watching it twinkle, watching it wiggle around at very high speed, and then you use a mirror to remove the twinkling of the atmosphere. Or, as is the case with Keck, you use a laser, you shoot it up in the sky, and you watch how the laser wiggles around, and then you can use that information from the motion of the laser to sharpen your image, to sharpen the images that you're getting from the telescope. So it's a technique that has been used for 20, 30 years now. I think it was originally developed by the military, of course. I think the Air Force was trying to get sharper images of satellites or something like that. But the technology is now commonly used by astronomers. It does have limitations. You can really only look at bright objects, and you can really only look at a very small patch of the sky using this adaptive optics technique. And also, you need to be at a site where the air is already very steady. So on a mountaintop observatory in California or Chile or Hawaii in this case. This is a real photograph. I mean, this looks like something fake. This looks like something from Star Wars, but this is an actual photograph of the laser guide stars from both Keck 1 and Keck 2 shooting up. And in fact, this is during observations of the stars around the massive black hole at the center of the Milky Way. And you can, this is a picture from Astronomy Picture of the Day, right? So you can see the URL there, and you can see the text, the explanation right down here underneath it. And there you see light reflected off, being scattered by the atmosphere from the lasers. So the lasers are much brighter than what they look like in this image, and showing, zooming in on the area around the center of the Milky Way. If we, I can see Sagittarius right there. So there's the teapot asterism right there. There's the spout, and there's the lid, and there's the handle right there. So just as I said, the supermassive black hole, the center of the Milky Way, is just above and to the right from the spout of the teapot. It's elevate. So someone's asking, elevation makes it better. Yes, being above, as high above as much of the atmosphere as you can, helps with doing infrared astronomy, and it helps with doing high resolution, really sharp astronomy. So they did not, the UCLA team led by Andrea Ghez did not actually see the supermassive black hole, of course. I've heard that the Event Horizon Telescope people have taken images of the supermassive black hole in our galaxy. This past summer, I talked to Angelo Ricarte, who is working for the Event Horizon Telescope team, the team that released the images of the Virgo A supermassive black hole a year and a half ago now. And I think they have images of the Milky Way black hole, but they're still working on it. They haven't been released yet. But what they saw were stars near the black hole. And so if you take these images, infrared light from these stars, you can measure their positions, and you can actually see them moving as they're orbiting around the supermassive black hole. This is amazing because we so rarely see motion from year to year of stars, especially stars that are really far away. These stars are about 25,000 light years away, near the center of the Milky Way. And so you see that they're following elliptical orbits around an invisible point. Now there's a star that marks the point that all of these other stars are orbiting around. Now these are actual near-infrared images of stars in the center of, or near the center of the Milky Way, in the bulge of the Milky Way. And they're following what we call Keplerian, after Johannes Kepler, who discovered that the orbits of the planets are ellipses. Keplerian orbits. And in fact, there's Kepler's laws of planetary motion, which are very old. They go back to the early 1600s. In the time of pre-telescopic astronomy, Kepler actually came up with these laws. I can demonstrate these to you quickly. So here's the sun right here. Here's a planet right here. This is actually a model for Mercury. And I can run a little animation here so you can see what the orbit of an object orbiting something very massive looks like. So here's a planet orbiting the sun. And Kepler discovered that planets can have different elliptical orbits. They can have more eccentric orbits, or more of a squashed oval-shaped orbit like so, or they can have more of a circular orbit like so. For example, I'll show you the orbit of Earth. All right, so Earth's orbit is pretty circular, and the distance from the sun to the Earth is what we say 1 astronomical unit. And then if we look at Mars's orbit, okay, so you can see that, yeah, Mars is definitely closer to the sun over on this side and further away over on this side. And so you can see what the squash factor is, what the eccentricity factor is for Mars's orbit around the sun. Something else that Kepler discovered was that planets speed up when they're close to the sun and slow down when they're further away. That's Kepler's second law. And then finally, Kepler's third law relates the size of the orbit to the speed of the orbit. So you can figure out how long it would take the planet to orbit based on how far away it is from the sun. Now, we now understand that this is due to gravity, right? This is something that's related to how strongly the mass at the center of the orbit is pulling on the planet. Or in this case, or in the case of the black hole, how that massive black hole is using gravity to pull on the planets. And there's a simple relationship. Kepler's third law gives you a simple equation that you can use to find the mass of the thing that's pulling. In this case, the mass of the sun, or in this case, the mass of this unseen, this invisible object that's causing these stars to orbit around them in these elliptical orbits. I try not to do too much math when I'm doing public talks, but I'll do a little bit of math here because it's not hard and we can do it. This is Kepler's third law. So the size of the orbit, if you cube it and then divide by how long it takes to orbit, if you square that, you get the mass of the central object, the star or the black hole or whatever it is that's pulling on the planet to keep it in orbit, or the star to keep it in orbit. Now, what's the size of the orbit? Now, that has to be sort of the average size of the orbit in units of AU, right? So if I were to plug in for the Earth orbiting the sun, the Earth orbits at a distance of 1 AU. And the period of the Earth's orbit is 1 year. So if you plug that into this equation, 1 cubed over 1 squared gives you 1 mass. That's the mass of the sun, 1 solar mass. And it should work for anything orbiting the sun, right? So let's see, Mars is in a 1.5 AU orbit, and it takes like 1.7 something, or maybe it's 1.6 something years to orbit. No, 1.75. That's pretty close. I'm about 10% off, but that's pretty close. It should work for Jupiter. Jupiter is in an orbit that's like 5.2 AU distant from the sun, and it takes about 11.9 years for Jupiter to orbit the sun. Yeah, so I get an answer that's 0.99, so 1 solar mass. So that's why the planets that are further away from the sun are orbiting more slowly. There's just less pull of gravity of the sun on that object. Now, for this black hole, what's the size of the orbit? Well, let's look at Let's look at this star right here that's on the yellow orbit, right? So star S0-2, it's on this yellow orbit. So it starts out really far, and then it falls in and whips around the black hole. There it goes, whoosh, and then it comes back out. And what's the size of its orbit? Well, it gets really close here, and it's really far away here. So it's kind of like the average size of the orbit is what you'd want to use. What's the average size of the orbit? Well, I can see how big the angle is. It's 0.1 arc seconds. What does that mean? Well, there's there's 3,600 arc seconds in a degree, and this is 1/10 of that. So this is really, really small. This is like the size of a quarter at about 50 miles away. So take a quarter, hold it at arm's length. That's like 2 degrees across. Move it to 50 miles away, halfway across the state, and then try to see how big it appears. This is why you need a big telescope on the top of a mountain with adaptive optics to see that fine of a detail. But we can calculate the size. I'm not going to explain the math in detail. Let's see, I think the orbit's a little bigger than that. It's like 0.12 if you sort of look at the size of that ellipse. And if I multiply that angle by the distance to the center of the Milky Way, which is 8,000 parsecs, it turns out that the size of that orbit is about 1,000 AU, about 1,000 times the distance between the Earth and the Sun. And what's the period? Well, for that guy right there, he falls in, swings around, comes back out, and it takes about, let's see, we go from about 1995 to 2011. So if we go from 2011 to 1995, that's 16 years. So it's about 16 years for it to do that loop. Wow, it's going on this big loop that's at a distance of 1,000 AU, 1,000 times the distance from the Earth to the Sun. What would that be in miles? It's 93 million miles for an AU, so it's 93 billion miles for that distance. That seems like a lot, but that's actually a really small distance, for something orbiting around in the Milky Way. What's the mass of the black hole? It's about 3.5. It's actually closer to 4 billion times the mass of the Sun. 4 million, not 4 billion. 4,000,000. I'm rounding up from 3.5 million here. 4 million times the mass of the Sun, and it's in a volume that's less than the size of the inner solar system. The only thing that can be that small and that massive is a black hole. So this is really strong evidence, really conclusive evidence, Nobel Prize winning evidence that yes, there is a supermassive black hole at the center of the Milky Way. So really exciting. Okay, well, that's my math and science lesson for tonight. If anyone has any questions, I'm happy to take questions. I'm going to show the black hole show. So this show runs for about 20 minutes. And I don't know if I should keep my camera open and interject with comments from time to time or just let it run. This is the same show that we've shown in the planetarium occasionally, but I've changed the format, I've downsampled it, so the quality is not nearly as good, and you're not seeing the sort of the same detail that you would see on the dome, obviously. But I think I'll just let it play. I mean, maybe I'll pause it occasionally to say something, or if someone asks a question, I'll pause and say something. So let me bring up the movie here and get it started. And I'm going to need some headphones so I can hear it. I think I'll make just a little quick introduction, and then I'll duck out and play the movie.
The Milky Way is just one of over 100 billion galaxies in the universe.
This is a movie from, I think it was produced in 2006.
And our sun.
So you'll actually see
100 billion stars.
You'll actually see a discussion of Andrea Ghez and her research team at Keck. And you'll actually see the models of the orbits around the center of the supermassive black hole. So we've known about that for a while. All right, I'm gonna let this play for a while. If anyone has any questions, throw them in the chat.
universe wields violence beyond comprehension. Forces capable of tearing space and time to shreds. I'm Liam Neeson, and we're going to take a trip to the dark side, straight inside a black hole. Cape Canaveral, Florida. Our quest to understand black holes is about to enter a whole new dimension. Tucked into the nose of a rocket is a telescope called SWIFT. Its mission? To hunt for perhaps the most elusive objects in the cosmos. Black holes are so dense, not even light can escape their gravity. They defy detection. But today, hopes are riding high.
8, 7, 6, 5, 4, 3, 2, 1. We have ignition, and we have massive SWIFT spacecraft moving mission to study and understand the
Scientists are counting on SWIFT to transport them to the frontiers of human knowledge and beyond. How do you find something that hides in the dark? You have to look for its telltale signs. SWIFT's instruments are designed to record bursts of high-energy radiation. Gamma rays don't penetrate Earth's atmosphere, but out here in space, SWIFT's view of them is front row center. They erupt when a black hole is born. That happens when a large star dies in a blaze of glory called a supernova. It's an explosion so powerful it's as bright as a billion suns. What triggers that chain of events is the force that rules the cosmos: gravity. Scientists used to think of gravity as some kind of mysterious power that objects like the sun project across space. But what if it's space itself that gives gravity its pull? That's the way one man saw it. To Albert Einstein, space is a bendable, four-dimensional fabric he called space-time. And gravity? That's the warping of the fabric by massive bodies. They literally put a dent in space-time. Objects get caught in their groove and simply drop into orbit. Einstein's theory was a radical notion, all the more when taken to its extreme. Just how warped could space get? Scientists found the answer in a singular class of star, more than 25 times the mass of our Sun. It's earned its name, a red supergiant. This star will live only a few million years, a fraction of our own Sun's lifetime. Deep inside, the crush of gravity sends temperatures soaring above 1 billion degrees. Lighter elements fuse into heavier ones. Hydrogen becomes helium, becomes carbon, on up to iron. The core grows so heavy, it buckles in on itself. Then, the collapse sends a shock wave roaring out. The star digs itself deeper into space-time as a black hole forms at its center, and the giant goes supernova. When the dust settles, what's left is a black hole, an object 1,000,000 times the mass of Earth, but 1,000,000 times smaller. A black hole is literally a puncture in the fabric of space-time. Venture closer, and gravity becomes a riptide. It's like riding a raging river that's pulling you faster and faster toward a waterfall. The closer you get, the stronger the current. You're headed for a point of no return. In cosmic terms, it's called the event horizon. Over this edge, there's no escape, not even for a beam of light. Black holes are gravity to the max, and yet they are altogether commonplace. Astronomers have actually detected dozens of black holes in our galaxy. They estimate there are tens of millions more. But then gravity doesn't stop there. It turns out there's a whole other breed of black hole out there. Peering into galaxies beyond our Milky Way, astronomers have found that nearly every one harbors an immense black hole at its center. One galaxy steals the show. It's called M87, and it's got a black hole 4 billion times the mass of our Sun. It has left its signature, a powerful jet erupting out at nearly the speed of light. Where does a hole this ferocious come from? To find out, turn back the cosmic clock 14 billion years to the beginning of the universe. The Big Bang. Matter and energy rush outward as the universe expands. To learn where supermassive black holes came from, scientists have recreated these early times with supercomputer simulations. They can trace the long, steady process that formed galaxies. From the start, gravity reigns in the cosmos. It draws together the primordial gases. These aren't gentle clouds. As they grow more and more dense, they heat up. Over millions of years, they become hot enough to ignite. The first stars are born. They end their lives in powerful supernovae, while their cores collapse into black holes. Billions of years later, and across billions of light years, Swift is today scanning the heavens for these same early supernovae. It's helping us learn what became of those black holes that formed in their wake. Astronomers believe some grew huge by plowing their way to the centers of their host galaxies, where they gorged on a rich supply of gas and stars. Some black holes grew larger still when they crossed paths with others. This scientific simulation traces the collision of galaxies, a drama that plays out over 2 billion years' time. The two galaxies become one. The black holes in their centers merge into a single powerhouse of staggering size. The gas hurtling into it gets jammed, heats up, and erupts in ferocious waves. Blast waves from supermassive black holes can stretch for thousands of light years into space. They may lay the framework of the new galaxy, sculpting its size and shape and stocking it with something unexpected. Black holes may be one of the chief ways galaxies get seeded with elements generated by stars, with carbon, oxygen, and iron, the stuff of solar systems, and us. So how did our galaxy make out in all this? Astronomer Andrea Ghez wants to know, have we got a supermassive black hole of our own? For more than a decade, she and her team have been coming to the heights of Hawaii's Mauna Kea volcano to find out. Working at the giant Keck telescope, Andrea is tracking a strange presence in the center of our galaxy. A group of stars is swirling around it, and she's clocking their speeds, projecting their orbits. Her telescope is so powerful, it can peer through the thick of the Milky Way, through 26,000 light years of cosmic dust, all the way to the stars at the galactic center. Whatever's got them in its grip, it's accelerating the ones closest to speeds of up to 3 million miles per hour. Given that, Andrea and her team calculate that the culprit weighs in at almost 4 million times the mass of our Sun. Solid evidence that at the exact center of our galaxy lurks a supermassive black hole. Andrea has confirmed the black hole is there without actually seeing it. So we're left to wonder, what's it like up close and personal? We can stop wondering and pay the monster of the Milky Way a visit. There's no spacecraft heading there anytime soon, but that's not stopping us. We'll get there courtesy of the latest telescope observations and computer models. We're just leaving the suburb where we live, about halfway out from the center of the galaxy. The Milky Way stretches before us. It's so large that it takes a beam of light 100,000 years to cross from one end to the other. Next stop, our galaxy's central hub, brimming with stars, known simply as the bulge. The farther we travel from our quiet cul-de-sac, the more crowded it gets. Up ahead, it's one big traffic jam of dust, stars, and hot gas, and it's always rush hour. Approaching dead center. The way is already strewn with signs of havoc. Supernova remnants and swirling clouds. Our course so far has been charted by astronomers like Andrea. They have plotted the landmarks by how they register across the light spectrum, from radio waves to X-rays. But here, their observations reveal a no-man's land, an inner zone cleared by the voracious appetite looming ahead. A cloud of super-hot gas is swirling around it. The black hole pulls the gas in, then spews much of it back out. Now things get really strange. What you are seeing is not the stuff of Hollywood special effects. It represents the first time scientists have visualized the journey into a black hole. Their guide is Einstein and what his equations tell them. Space here is so warped, the black hole acts like a giant lens, twisting the light that scatters across it. At last we cross the event horizon, the point of no return. But don't expect the inside of the black hole to be dark. Swirling within is a maelstrom of energy and matter. Hidden in the chaos is a single point where the black hole's mass is packed, known as the singularity. Now imagine there's an eye to this storm, magically made calm, so all the strange predictions of Einstein's equations can play out. We'd be greeted by a passageway, an escape hatch in space and time known as a wormhole. Through it, we enter a white hole. Here, the same twisted logic holds in reverse. Instead of being drawn in, all light and matter are flung out. But to where? A wormhole is just the thing for a science fiction character in need of a quick getaway to another universe. Unless the truth be told, the inside of a black hole is too violent a place for a wormhole to actually form, let alone for the likes of us to venture. This is nature's ultimate fury. Destruction on a scale beyond comprehension. Or is it? In fact, it's simply the workings of a restless universe. A long time ago, when this black hole was young, powerful winds roaring from it seeded our galaxy with elements. They may have helped form a sun and planets, and some beings who could look into the sky and ask, what is a black hole? Our search for the answer is turning up dark mysteries and radiant revelations. Secrets stolen from the other side of infinity.
Okay, well, seeing this show makes me think about, reminds me of doing planetarium shows in the planetarium with actual people back in the day. Hopefully, we'll get back to that before too long. Planetarium shows in the planetarium theater. This show is getting a little bit dated, right? So, you know, if someone were doing a black hole show now, they would certainly talk about the discovery of gravity waves from merging black holes that happened a few years ago, and the Event Horizon Telescope images of the M87. We flew through the M87 galaxy, and now we have an image of the event horizon of that black hole. And then, of course, this announcement about the Nobel Prize for the black hole discovery and some other important discoveries that have been made. I still like the animations and the graphics. A lot of them are based on real science, real observations from radio telescopes and infrared telescopes and optical telescopes. And I think especially the flight from the sun to the center of the Milky Way is pretty accurate. I think it's actually, I mean, if you could do it in a way that would be dramatically fast, so you could see it over your lifetime. You know, if you could imagine doing such a thing, it would look more or less like that, going through the spiral arms and then into the bulge and seeing the dust clouds and seeing the stars in the bulge and seeing the black hole. And the producers of this movie actually did the calculations, the math of the predictions of general relativity, how warped space would act like a lens to refract the light from stars in the background and produce the images that you see in the movie. The producers of the movie Interstellar did the same thing when they were working out how light would appear around the black holes in Interstellar. So you could do the math and have computers calculate how those black holes act like lenses, and what you would actually see. All right, well, I'm going to have to stop there. So if anyone has any questions for me, I'm happy to take any last questions on the chat. One thing that I don't like so much about this show, there's two things I don't like about it as much. One is the ending, I think, is a little bit weird and maybe a little bit hokey. There's no such thing as a wormhole or a white hole where you would come out of a black hole. I think the producers, the writers of the show, put that in because once the audience crosses the event horizon of the black hole, they're never coming out, and that's depressing. So let's get out somehow. Go through this imaginary white hole or wormhole. Wormholes can be described in general relativity, but there's no way they could actually exist in nature. They would collapse at the speed of light. There's no evidence that there are wormholes, that the supermassive black hole at the center of the Milky Way has a wormhole. Okay, well, I'm going to stop there. So thanks for your attention tonight and for watching the live stream. I'm trying to do this every Tuesday night at 8 p.m., talking about what's up in the sky, talking a little bit about astronomy news, taking questions from anyone who happens to be watching live. And then if the sky's clear, I'll go out and set up telescopes outside and we can look at interesting things. The planets that are out, we've got 3 naked eye planets out at sunset right now. So lots of interesting solar system objects to look at. And then we might look at some other star clusters and nebulae and galaxies as well on a clear night. All right, so my name is Michael Faison. You can send me an email if you like, michael.faison, Faison, at yale.edu. And the Leitner Observatory website is Leitner Observatory, Leitner, observatory.yale.edu. So if you go to that website, you can see links to the live stream, and if there are any upcoming events, news about when we might open the observatory to the public on clear Tuesday nights. I imagine that at some point we'll be able to have people come with masks and standing at certain distances from the telescopes, and it'll be safe to use the observatory for public outreach. But it may be a while before we can use the inside of the building. Okay, all right, thanks Fred, thanks Richard. I don't see any questions, but